Matematika. Today we're going to do 1.14 Function Model Construction and Application. Recall that we begin the modeling cycle by clarifying the problem, as what we did in 1.13. So to do this, we identify the problem, that is modeling with functions. So restate the problem to clarify what the model intends to measure, predict, and or solve. Identify the question that we need to be considered, and list factors that will affect outcome, and research information needed to answer the problem. Then state the assumptions to narrow the focus. The next is create a model. The model is created. Models can be presented as equations, graphs, tables, diagrams. Certain types of functions relate to certain types of real-world situations. So we have studied the following functions types, like linear, that including the constant and absolute value, exponential, polynomial, including the quadratic and cubic, rational, trigonometric, radical, logarithmic. Okay, that is when we create a model. After creating a model, we apply and analyze. After creating a model, it is important to analyze whether the model accurately represents the situation in the context. If the model is not accurate representation, then we need to adjust the model or decide on a new type of model. Next is interpret results. Then we interpret the results that come from applying the model. Interpreting results includes the following, like determine whether the answer makes sense in terms of the context, identifying any extraneous solutions from the model that do not apply to the situation. Next, we verify. We verify the model works as intended. Okay, verify. Discussing its potential accuracy depending on the limitation of the model or assumptions we made when creating the model. If the model does not work as intended or is not accurate, we adjust and improve it as needed. If the model works and is accurate, we draw any relevant conclusions to the context. And the last one, report findings. This is where when we make conclusions based on the results, we should be prepared to report our findings. Reporting a model would include information that is relevant to the audience and enough detail that the audience understand the reasoning behind any recommendation. So reporting a model does not include technical algebraic work or mathematical jargon that could confuse the audience. Okay, these are the modeling with the functions. So there are 6 of them. So this is what we're gonna do in the examples that we are having here. Let's have example number 1. Rainfall analysis is important to help manage and prevent flooding. The amount of rainfall during a storm in Pearson, Florida was recorded over a 2-hour period. This is over a 2-hour period, and the data is displayed below. So we have time in minutes, 15, 30 up to 120. And the rain in equivalent rain in inches. So suppose we need to find the time interval when most rain accumulated, how much accumulation or accumulated during the time. So first of all, the first step is to identify the problem. Okay? Identify that problem. State any assumption. So, to identify the problem, we need to clarify what model intends to measure, predict, or solve. So, some questions that we may need to consider is, when did the storm begin and end? And how do these times relate to the times when the data was collected? That's one question. How will most rain accumulated be defined? Is the amount of rain that accumulated a cause for concern? So since we cannot research the specific storm or assumptions, we need to make about when the storm began and ended, and how this relate to the times when the data was collected. Also need to make an assumption what most rain accumulated means. Okay? So let's assume that the data was collected shortly after the storm began and that the storm ended shortly after 2 hours. One assumption that we could make is the storm began at 0. Okay? Begins the time at 0. So there were 0 inches of rain when the storm started. So this is like our assumption, and we identify the problem. The next is create. Okay? Create a model, a new model to represent the data. So by plotting the data, right, we have these points right here. And then you were given the data in the table, but the form may not help us determine the specific times when the rain accumulated faster or slower. Instead, we begin by plotting the data in the graph, in the coordinate plane, and use the graph to help us create an equation. So for example, the data has been already plotted here in this graph. Okay? Then looking at the shape of the data, it appears that it's like you have an accumulation right here, and then there's a space. There is another one right here. So if we try to connect that, we come out with that kind of graph. So it appears that it's a cube root function. Since the rain accumulates slowly, it can be a good model. Since the rain accumulates slowly, then accumulates quickly, then slows down again. Slow, fast, then slows down again. Then accumulate quickly, then slows down again. So we can transform, since it's a cube root function, we can have the parent function as y equals the cube root of x until we find an equation that appears to fit the data well. So we can have this as the amount of rainfall from the particular storm. We can model the equation by 0.15 cube root of x minus 65 plus 0.6, where x is the time in minutes and r is the total rainfall in minutes. R is for the y and x is for the time in minutes. Okay, we can use this equation right here coming from our parent function. So the question is, where did we get that 0.15 and x minus 65 coming from? The x value here that is inside the radical sign, and 0.15, we're gonna find that out as we move on, where we are going to do this equation right here, plus 0.6. All right, let's do the C. Apply the model to find the time interval when most rain accumulated and how much accumulated during the time. Interpret the result. At this point, we will need to decide when we think the rain started accumulating more than it did at the beginning of the storm. When it starts to slow down again, it's important that we highlight the assumption when stating the result. Okay. Since the cube root function are symmetric about an inflection point, so if we try to look at this, we come out like it's like a parabola facing up, and then it goes, the curve changes, the parabola facing down. So there is an inflection point wherein it's the center of the graph. We should choose an interval such in the middle of the value of the interval is the center point of the graph. So according to our model here, the center could be x equals 65. So 60, 75, so this might be 65 right here, and this will be 70. So if I move this up, it could be here at this point. Here. So it appears that most of the rain started accumulating about 10 minutes before and after 10 minutes. So before 10 minutes and after 10 minutes, you can see that it started accumulating here at this point, which was between 55. So where is this is 50, 55. 55 is somewhere here, and 75. So from here to here, that portion, minutes into the storm. So substituting this value, all right, so we're gonna use the function that we used, 0.15 cube root of x minus 65 then plus 0.6. All right, because somewhat like it's somewhere in 0.6 with the accumulation. So that would become 0.15 cube root of the x would be 55 to 65 plus 0.6. Then computing, it's approximately 0.2768. Just use the calculator to find the cube root of 55 minus 65. That's negative 10. All right. And the other one is R, 0.15. That is 75 this time, minus 65, plus a 0.6. So approximately the value is 0.9232. This is from 55 to 75. Okay. Next, we will subtract these values to determine how much rain is accumulated over the time period from 55 to 65. We're going to find how much is the accumulation. So in other words, 0.9232 minus 0.2768, that's the accumulation when it's 55. That would be equals to 0.6464. Therefore, we could say that about, we just round this up, about 0.65 inches of rain accumulated between 55 minutes and 75. 55 minutes and 75 minutes into the storm. So there is an accumulation of 0.65. So this tells us, although the storm lasted 2 hours in total, it rained the hardest during the 20-minute period in the middle of the storm. This might be between the 20-minute period between them in the middle of the storm. So these results are based on our assumption about when the rain accumulated faster when it slowed down. Others may assume at different time interval, larger or smaller, which would have produced different results. So this is based on the assumption. Verify the model works as intended and improve as needed. So to verify the model, we need to determine whether the model answers the question we need to answer or whether it answers the question accurately. So we will also need to discuss the limitation. So the model is also or was designed to determine the interval when most rain accumulated. And it does satisfy this need. However, the model is limited to the data collected, and some data collected on this particular storm and cannot be used to analyze the rainfall for basing on the data collected. So this model is also limited to the data collection process used. So the data was collected during the 15-minute interval, or this means there is a lack of specific data on how the rain accumulated during most of the intense part of the storm. Although the shape of the model may not be completely accurate between the 60 to 75 minutes of the storm. So the result when most of the rain accumulated is fairly accurate. So model collected data collected on this particular storm, or the model can't be used to analyze the rainfall from any storm. Create a report. This is now for the report about the particular accumulation of rain during the storm. So you can use like coming from the internet or the data to support your report. So in this case, from coming from www.britannica.com, rain is classified in the following ways. This is now creating a report. Light is less than a 0.1 inches per hour, moderate between 0.1 and 0.3 inches per hour, and heavy is more than 0.3 inches per hour. That is the classification of the storm from coming from the internet. So we could say for our report that for the first 55 minutes of the storm, the residents of Pearson, Florida experienced a moderate rainfall. Next 20 minutes of the storm, there was a heavy rainfall. So the 20-minute interval, majority of the rain accumulated amounting to 0.65 inches. So if we go back to the table here, we could say where it rains fast with the time interval here. That is where the accumulation can be determined. The remaining 45 minutes, there was a moderate rainfall of the storm. Suppose the storm did not stop after 2 hours, but continued to rain. Okay? Steadily for another hour. By the end of the third hour, a total of 1,452 inches of rainfall had accumulated. With this information, determine whether your model would need to be adjusted, and if it is or if it does not need to be adjusted. So our current model, to determine the amount of rain, we have the R, which is equals to 0.15 cube root of 180 minus 65 plus 0.6. This is for our current model. Okay, let me see right here. I have to go back. This is only up to 120. Okay. So this is approximately, by doing the math, approximately 1.329. This is not consistent with the new idea. So we will need to adjust the model because it's not consistent. Since the cube root model accurately represents the first 2 hours of the storm, we can use a piecewise function model to determine a new equation that models the third hour. So we'll use a piecewise function model. This is now up to 180 here. All right. And determine the new equation. By using the function of piecewise function model, we can determine the new equation that models the third hour storm. So, by doing that, we need to find the equation of the line that passes through 120 and 1.158, somewhere here. So we could use the slope y2 minus y1 over x sub 2 minus x sub 1. So we can have let's say 1.452. That's the accumulation here, 1.452 minus 1.158 over 180 minus 120. So if we try to look at the 120 right here, just estimating, all right, just estimating how much would that be, 1.158, closer to 1.2, and the other one is 1.452. This is somewhere here. $1.452. Right. So computing, you have a 0.0049 after evaluating. So y would be the slope, the y-intercept form, equation of the line would be 1.452, that's the y, 0.0048, that's the slope, times 180, the value of x, plus b, the y-intercept. Okay, so how much the y-intercept would be? 0.57. That's the value of y-intercept. So the equation of the line would become y equals 0.0049x plus the b, which is 0.57. You multiply 0.0048 times 180, and then you divide it with 1.452 divided by the result when you multiply 180 by 0.0048. And this is the equation of the line. Therefore, the piecewise model, we can have the r, we could use that as 0.15 for the first one, cube root of x minus 65 plus 0.6 in such a way that, okay, I have to write it somewhere here. Oh, I need a longer space. So r, these are our piecewise function, 0.15 cube root of x minus 65 plus 0.6. The x that's between 0 and 120. And the other one is 0.0049 x plus 0.57. X should be greater or equal to 180. So to check if our piecewise function was okay, um, we have to look at it in the graph right here. So the equation appear to be the model of the data well and more collected. Models will often need to be adjusted. Okay, that is how it should be. Okay, that's problem number 2. To start a freeze dried candy business, Carly must purchase a freeze dryer and then supplies like candy, packaging, and labels for each product they sell. Okay. So letter A is create a function that models Carly's cost. So that's the first step that we're going to do. All right, let's do this. So we will need to research the cost when we want to create. How much is the cost for freezer, dryer, freeze dryer for a candy? Uh, from the internet, from the internet, we could find a home freeze dryer that is costing like costing $2, 495 and 5,090. The cost of candy varies depending on how much purchase and how it's packaged. For this model, we'll use 30 pack for individual truly candy packs that can be purchased for $25, making its bag for about $83.83. Again, there are a lot of packaging choices out there. Carly can choose from the model. So we pick a pink stand-up pouch that is like 5.85 inches by 3.5 by 9.0125 inches and is advertised to hold 6 to 11 ounces. Carly can buy 100 bags for $42, making the cost of each bag as 0.42. So Carly only needs to buy the freeze dryer once, then she will need to spend she will need to spend 83 cents plus 0.42, that goes to 1.25 for each bag, per bag of freeze-dried candy she wants to make. This is of freeze dryer. This is a freeze-dried candy. Freeze-dried candy, I mean. Alright. Now we'll assume that the candy packaging won't vary over the time, which means we can use linear function. Okay, This is the plan. We create the function. We can use linear function to model the cost. To model the cost. So what will we do? Let x represent the number of bags. Right? Represent the number of bags of freeze-dried candy. What else do we have? Dried candy that Carly produces. So then we could have the Carly produces that amount of candy would be 125x. That is the number of bags plus 5,000. This represent the total cost. Okay, total cost, assuming she buys a more expensive freezer, which is the 5,000. And that would be the equation that we are going to assume. So some assumption, we could consider Carly's costs are $1.25, but she planned 150 to account of any unexpensive changes. So let's find out which one is more accurate for the assumptions. Determine if there is a reasonable price for that. So this might be the assumptions, other assumptions. It could be, let's say, the first assumption we had is $1 per $1.5 per bag plus 5,000. So you can have that. If she purchase a cheaper, she can have the cheaper freeze dryer. She can have 1.25 per bag plus 3,000. And another assumption, she can have 1.25. If she needs to pay 100 for a business license and pays a graphic designer for 150 for a logo, then she has to spend more, 250 more from added to the freeze dryer for the candy. So these are the assumption. Determine a reasonable selling price and create a function to make the model. So let's say we consider the market price of freeze-dried candy for the other sellers. How much would Carly wants to earn for each bag sold? For her profit margin, and how long would it take her to pay off the initial cost before she makes a process? We'll have to think about it. There are companies online selling freeze-dry candy bags between $10 and $12. And then when she went to her local farmer's market, Carly saw someone selling freeze-dry candy for $8 per bag. So Carly revenue function would be, if she buys the $8 per bag, it would be C times X, where C is her cost per bag. For now, let's just assume a cost of $10. okay, which is in the middle of what she found between 10 and 12, and then she found 8. So 8, 10, 12. We'll just have the $10, we assume. So which is in the middle. So that means we can use the R times X, which is 10X. Okay? So we'll combine the functions of A and B. This function here and this function that we have here, we combine. And then combine your functions from A and B to create a function that models the business owner's profit. Okay. So the profit is the difference between, we have to know that the profit is the difference between the revenue and the cost, right? So that's why you say, oh, I gained something here, deducting from the principal amount and the cost that you spend, or the revenue and the cost. Carly's revenue function. What is Carly's revenue function? That is the equation in B. Okay, that is how much she bought for its bag, is R of X equals 10X. And her cost function is equals to 1.25x plus 5,000. So her profit function would be, that is the profit function, would be the R revenue function minus the cost function. So that would be 10x minus 1.25x plus 5,000. So substituting and subtracting, we come out with 10 minus 1.25, that is 8.75x minus 5,000. So the profit function would be 8.75x minus 5,000. That's the profit. So use your cost, revenue, and profit models to write a business plan. So Carly needs to know when her business will start profiting. We should also present her with a few reasonable options. So we have the option right here. If Carly purchases the 5,000 fridge dryer and sells her candy at 10 per bag with a 1.25 cost per bag in material, she will sell 572 bags to pay off her initial cost and start profiting. If she purchases a cheaper freeze dryer at 3,000 and keeps her selling price the same, she can begin profiting after only 3 bags sold. Okay? If Carly buys more expensive fridge dryer, increases cost per bag with 150 and sells the bags at 12 each, she will need to sell 477 bags to start profiting. Okay. So this is the graph how it shows. Starting from 5,000, if you look at the green and the purple line right here, and starting with 3,000. Which one? The 3,000 is the blue one. In summary, what do you expect to make between 300 to 600 bags of candy before she makes a process? So what can we recommend that to Carly? Purchase the most reliable machine at the cheapest price. Take advantage of the bulk pricing plan to buy supplies for making the least 600 bags of candy to stay out of debt. So find the highest selling price cost that still gets her the business she needs to succeed. So which one would we prefer to? Starting with the cheapest, this one. All right. Let's have the third problem. Kala wants to build a fruit and vegetable garden, her family's backyard. To support her ambitions, her family bought 300 feet of fencing for her to use. Kala wants to separate the fruit from the vegetable. So her plan is to build an enclosure that is separated down the middle by a row of fence. Okay. Carla plans to use um, the available fencing to create her garden. She is debating between a circular and a rectangular garden. Okay. So we're gonna start. You're asked to create a model to represent the perimeter and area for its garden type and define your variables and discuss any constraints. So to help the visualize the situation, if she plans for a rectangular, this is for rectangular plot. Okay. Because Kala wants to separate the fruit from vegetables with a row, we need to include the part of the fence in our calculation. So perimeter will be the fence around and outside and the fence on the inside. So we let x represent the width of the rectangle, which is the same length as the fence in the middle. Let y, so I say here, let x represent the width of the rectangle. And then y represent the length. I'm not right, represent anymore. Y would be the length of the rectangle. Okay. Then the equation of the perimeter is the sum of all the lengths of the side of any, okay, around and outside, inside, you get the sum. So that means we have 3x, this length, perimeter would be 3x plus 2y. And we have the length of the fence, which is 300, and that would be, could use that to equate the perimeter, 3x, or I could say like this. I would place the 3x plus 2y equals 300. The area function, okay, let's look at the area. Area is length times width, right? So the area of xy would be xy. That's for the function. So if we solve the parameter equation for y, we get 3x plus 2y equals 300. So 2y would be 300 minus 3x. We wanted to have an equation for y. That would be the 300 divided by 2, that's 150, minus 3 divided by 2, that is 1.5x. Okay, so we substitute 150 minus 1 point in x in the formula for the area. So the area for x would be 150 minus 1.5x. So this will be 150x minus 1.5x squared. Because x represents the length, we must know it must be a positive value. So we determine the upper limit of x by finding whenever the function is greater than or equals to 0. So we'll use that upper limit. It should be greater than 0. I will have the upper limit written to be here. 150 minus 1.5x should be greater than 0. So 150 greater than 1.5x. So 100 greater than x. This means that x should be greater than 0 and less than 100. So for the circle, let's look at the circle here. The circle, the perimeter can also be represented outside the circle, and the circumference plus the fencing that goes down in the middle here. Take note that the diameter is 2 times the radius. So let R represent the radius of the circle. Then the perimeter of the circle would be 2 pi r plus 2r equals 300. That is, we have the middle here. This is a 2r. The circumference plus the 2r. That is the perimeter. Since one variable, we can also solve for r. So to do that, 2 pi r plus 2r equals 300. So equation for the perimeter, 2 is common. So we divide this by 2, divide by 2, divide by 2. This will become pi r plus r equals 150. So r is common. Pi plus 1 equals 150. Factor out r. So r would become 150 divided by pi plus 1. And pi, we can use that by computing math. R would be approximately, pi is 3.1416. Approximately that value. 36.218. The area of a circle, okay, the area of a circle is pi r squared. So computing for the area of the circle, if it's a circle, we're trying to compare the rectangle and the circle plot. So this is the circle plot. Alright, so area would be pi times 36.218 squared. So the area is approximately 4,120.964, getting the 3 digits. So with 300 fencing, a circle with an area of, okay, let's look at the area of 4,120.964, about the area of the rectangular plot. So with 300 feet of fencing, a circle, okay, with an area of 4,120.964 feet squared can be constructed. Analyze your models to determine which type of garden Kala should make and include the dimensions of the garden and give the mathematical contextual arguments to defend your choice. So, to answer this question, we need to make an assumption about what key features Kala and her family might prefer. A rectangular shape is typical and may be easier to create, or may be better fit a plot of land. A circle may waste space, or it may be difficult to plant seeds around the edge of a circle. But maybe Kala isn't concerned with the shape. Maybe she simply wants the shape that has the largest area. So in part A, we found the area of a circular garden with the amount of fencing available is about 4,120 feet. Okay, this is feet squared. Graphing the area of the function, we try to graph the area of the function here. A rectangular, this is the circular garden with the amount of the fencing available is about, area is about 4,121 feet squared. Graphing the area function of rectangular garden can help us make dimension about selecting the shape Kala should choose the garden. So finding the vertex, or looking at the garden graph of the maximum area, is about 3,000 right here. The maximum. About 3,700 Let's say, let's approximate it, feet squared for it. So the area of the rectangular garden will always be less than the area of the circular. Rectangular garden is less than, this is area of circular garden. Okay. So let's assume that Kala prefers the gardening in rows. Although the circular garden has more space, the edges of the circle might end up wasting the space, which would make the area similar to the area of a rectangular. Since they might end up wasting the space, that would make it similar to the area of a rectangular. So the difference of few hundred square feet. With this factor, Kala should build a rectangular garden, assuming she wants to maximize the area. So we can use the x value of the vertex of the parabola to find the width of the garden. So the width of the garden should be 50 feet and the length of the garden would be, okay, would be 3x plus 2y equals 300. This is the parameter. So 3 times 50, let's say the width should be 50 feet. So 3 times 50 plus 2y equals 300. So 150 plus 2y equals 300. 2y is 300 minus 150. 2y is 150. So y is 150 divided by 2. It's 75. So therefore, the dimensions, all right, of the rectangular garden would be 50 feet by 75 feet. This is the dimension. Because this graph right here is the graph that we assume when we try to graph the function made in a circular, circular fencing. Circular has a greater area, but the edges will just take doesn't consume the space. Is not, if we think about the space is not suitable for planting the fruit and the vegetables. Okay. Our original diagram and equation models represented this situation accurately. But when we analyze our model and choose a garden shape, we realize that a graph was also helpful to visualize the situation. Sometimes one type of model alone is not sufficient. So find a solution. Multiple models were used to make sense of the problem, including the diagram function. All right. Okay, let's summarize the whole thing in this lesson that we have. When modeling real-world contexts, we want to remember that models are not perfect, but they provide an opportunity for us to interpret the world around us each time we model a real-world situation. We should, 1, identify the essential features of the problem, 2. Create a model using a diagram, graph, table, equation, or expression or statistical representation. 3. Analyze and use the model to find solutions. 4. Interpret the result in the context of the problem. 5. Verify the model works as intended and improve the model as needed. 6. Report on our findings and the reasonable behind them. All right. So this end up of our Unit 1, 1.14 for AP Precalculus. So in my next video, it will start with the Unit 2. So let me say this. If I can do it, so can you. Please don't forget to hit the like button and subscribe button. See you in my next video.